Hi everyone, welcome to Digital Srini channel on YouTube, and if you haven't already done so, please pause the video, subscribe to this channel right now. In this video, I'm going to talk about TensorFlow Lite, and as the name suggests, it represents a light version of TensorFlow. What it is, why do we need it, I'll talk about that in a minute. And I'll also walk you through the process of, meaning show you the code of converting your Keras trained models into TensorFlow Lite models so you can deploy them on any device that you want. And I'm going to use an example that we are a bit familiar with, especially if you watched my videos in the past. This is going to be a binary image classification example. So this is, we have a whole bunch of malarial parasitic images in one folder and uninfected cells in another folder. So we'll define a quick, easy binary classification and then train it using deep learning. Take that trained model, convert that to TF-Lite, and then infer or make predictions using the TF-Lite. And along the way, we'll learn a little bit about TF-Lite. Keep watching these videos because in the next one, I'll talk about face detection. And in the one after that, I'll talk about face detection plus emotion, age, and gender detection. And the one after that, we will deploy this face detection and gender detection onto a Raspberry Pi. And then see, for that, we of course are going to use TF-Lite. So this is going to, create some sort of a basis for you to understand the upcoming tutorials. Now let's try to understand what TF-Lite is, right? I mean, what is the need for TensorFlow Lite? First of all, deep learning models can be pretty huge. If you ever trained a model and saved them, right? These can be anywhere from 10 megabytes to 100 megabytes to 500 megabytes to gigabytes or even larger. I'm not saying you can take a 10 gigabyte model and then deploy that easily into a TensorFlow Lite, but hopefully you know that these HDF5 files, for example, that you save when you train Keras, a Keras model, they can be pretty large. And they're very resource intensive. So if you would like to deploy them on edge devices, what do you mean by edge devices? A phone is an edge device. If you want to use, machine learning on your phone, there are two ways. One, you can create an app that talks to a server, uploads the data to the server, and the server gives back whatever the response is. Nothing wrong with that, except that's slow and may not be secure enough. The second way is just infer it right here. Use machine learning, deploy machine learning trained model onto your device, and then make predictions right there. This is exactly where TensorFlow Lite can definitely help out. So deep learning models are resource intensive. So deployment on these type of devices, if I put 1 gig on this, I lose 1 gig, right? I mean, of storage. Storage is very important on my mobile devices. So that's one reason. The other one is these inferences, I already mentioned that, they are made on the edge device itself, like on these devices, whether it is a phone or your Raspberry Pi, they are made on these devices to eliminate the need for upload and download. Yeah, so just think of deploying it, even if there is no Wi-Fi connection. How can we infer, right? So that's the other reason. And also for most devices, data cannot be uploaded for security purposes. For example, you invent or you come up with an app that can take pictures of, I don't know, some sort of a discoloration, and then it says, okay, what is the probability of that being dangerous or cancerous, whatever you want to call. Then you don't want to upload patient data, to some server and then get the result back. You really want to keep everything on the device and then make the predictions. So that's another reason why you probably need a solution for these models onto these edge devices. When I say edge devices, again, the end thing, it can be as simple as a camera that senses your car is approaching the garage and then automatically, triggers the garage to open, right? It's up to you, your need. In fact, you can do that with your Raspberry Pi. It's a fun exercise if you really want to do that. So now moving forward, edge devices usually have also low power consumption, right? You don't want your batteries to drain. I mean, this can be powered to the wall, but what about your phone, right? So you need low battery power consumption. So you cannot, again, this need to be a lightweight and efficient solution. TensorFlow Lite is addresses these, I should say. It's the lightweight version specifically designed for deployment on these edge devices. And you can think of these, I just gave you an example of mobile platforms, but this can also be embedded devices, right? An embedded device like microprocessors that take decisions based on whatever the machine learning classification is providing to them as input. And the typical workflow for TensorFlow Lite looks like, I just Google searched for this image online, and then so this is not a graphic. I should have actually put down the source here, but just to let you know, this graphic, it's not mine. Okay, but the workflow, I mean, I like the way they presented this. That's why I kind of copied that to communicate about it. So initially, what do you do on your desktop, on Google Colab or Amazon Web Services, wherever you have a lot of resources, you train a model using TensorFlow or Keras. Right. So this is, I mean, of course, you can use PyCharm, but that's a different, PyTorch. That's a different discussion. But let's stick with TensorFlow. So when you train your model using TensorFlow, this model is a bit bulky usually. Now you want to deploy that onto your edge devices. So the process is you convert the model into a TensorFlow Lite model, and then during the conversion, you can optimize the model. Further optimize the model. Okay, optimize is just a fancy term, but just to give you what happens is, for example, if your model let's say takes in floating point numbers, that requires a lot of memory, right? So what if you say, okay, that's fine, let's just approximate that to integers. That's a way of optimization. You will probably compromise the quality of the result a little bit, but if that makes it possible for you to deploy the solution, why not? Yeah, without giving away too much of quality. So optimization, again, I'll talk about that in a second. You do the optimization while saving your model, and you deploy the model at the edge. And again, once you deploy it, of course, that model is now making predictions or inferences on the edge device. So in this video, I'm going to show you training a model for our malarial detection. Even in the next video and the video after that, we will focus on this part, like TensorFlow part. But in this video, I'm going to show you how to convert the model from a Keras HDF5 to a TF Lite, and then include the optimization as part of your saving process. And then we are not going to talk about deploy at edge and make inferences at edge, but we are going to deploy or make inferences on our Windows system. Yeah, so that's the plan for today. But then these parts, like making inferences on the edge using Raspberry Pi, let's save that for a couple of tutorials from now. Okay, it's time for us to jump into the code and get started. Okay, so let's arrange these a little easier for you guys to see. Okay, I hope this is easy for you to see. Now, there are three files I'm going to talk about. The first one, malarial binary. This should be nothing new, especially if you know deep learning. This is not a deep learning tutorial, right? This is not a tutorial about how to create a binary classifier. This is as easy as it gets. And watch my previous videos on this topic. But I will go through this at a very high level. But the goal of this first Python file is to train a model and give us the H5 file that we want, right? I mean, we are going to save this malarial model after 100 epochs, which I already did. I'll go through the code. And then next file is taking that malarial model and saving that into a TF Lite file. You see, just 3 lines of code, not difficult at all to save this into TF Lite. And then finally, let's take that TF Lite and start make some predictions. Yeah, so you can see how, what are we compromising? I mean, is the quality actually compromised? So let's get a quick understanding of that. So that's the plan, starting with our malarial binary here. So this problem, I have 2 folders here. One is parasitic, one is uninfected, and as you can imagine, the parasitic contains a whole bunch, 500 images of all images that are basically infected or parasited. You can see those right here. And uninfected, as the name suggests, these are all clean, nothing uninfected. So as simple as it gets when it comes to binary classification. So given that knowledge, let us go ahead. I forgot to change my working directory. Let's see if I did. No, I was working on a different thing earlier. So the easiest thing to do is let's run this file with some mistake, and it changes the directory automatically, right? You guys know that about Spyder. Okay, so we are in the right directory there. So let's go ahead and run these lines. Again, these are just our libraries, nothing new, sequential method to create a basic model. So let's go ahead and run these lines pretty fast. And now my image directory is cell images. Let me make sure that's the right thing. Under cell images, I have parasited and uninfected. And all I'm doing here is going through all the parasited and uninfected directory, loading each image using OpenCV, and then resizing them to 150 by 150. That's how I define my model. And I'm appending a label of 1 to the parasited and a label of 0 to the uninfected one. So let's go ahead and run this. Even though I'm not going to train a data set, it makes sense for us to do these so we can kind of verify how the results look like. Okay, so once that is done, I'm going to convert the list right there into a NumPy array, and then split my NumPy arrays for images and masks into training and testing data sets. Pretty straightforward stuff that we do all the time. So I have 1,000 images, 500 for uninfected, 500 for parasited. Each image is 150 by 150 by 3. And my labels, I have 1,000 labels, one each for each of these images. Okay, now let's divide our XTrain, our data, into XTrain and XTest. So 80%. 800 images for training and 200 for testing. And let's normalize these images. Again, you can scale them by dividing by 255. You can do min-max scaler. I chose to do normalization here. Again, that's up to you. And this is a simple model that I defined. So 150 by 150 by 3, a convolution layer, another convolution layer, another one going from 32, 32, 64. You can try your own. Dense layer, and finally the prediction layer. And I'm using sigmoid because this is a binary classification, right? So we get a probability between 0 to 1, and we'll set a threshold somewhere in between to separate this into classes, the probability into classes. If you don't know what I'm talking about, I don't think this video is for you, frankly. I want all the viewership I can get, but if I know that you don't have certain basic knowledge, like knowledge in NumPy or Pandas or what we are talking right here, certain terminology, don't waste your time. Go back to the basics, watch earlier videos, get yourself educated, and then come back, right? Okay, so let's go ahead and define the model and compile the model. I'm using, like I said, the sigmoid right there, binary cross entropy. Again, this is a binary classification. Okay, after that, I trained this for 100 epochs, and I have already saved the model. So I'll jump down and let me go ahead and select a test image so we can test it. Yeah, so here is a test image right there. And let's go ahead and load the model that we just saved. Let's load it and then check the accuracy right here. I don't know what accuracy we're getting. We're getting about 86% accuracy, not bad on this data set, even only with 500 images in each class. In fact, only 400 images in each class. Okay, so now let's just threshold let's just look at the confusion matrix just to see how good we are doing. So not bad, 90, 84, positively identifying, and then 14 and 12 are negatively, not positively identifying. Okay, so that's so far so good. I think that makes sense. And again, we can go into details. Why did I choose a threshold of 0.885? Why not 0.5? I thought of skipping that, but just to show you, I plotted the ROC curve. Hopefully you know what ROC curves are. And then I figured out what that point is, because this is the point that closest to 1. This is the one that, wherever the threshold is right there, that gives you the best split between true positives and false negatives and all that. So I found that out, and I think that's exactly what I got. It has been a while since I tested this code, but you see 0.866. is the ideal threshold. That's exactly what I ended up using. Okay, so far so good. What do we have? We trained a model and we have a H5 file. That's it. Now we need to convert that into TF Lite and then start doing our predictions. I'm not doing serious predictions here. I just looked at the quality of my model. I'll do predictions along with the TF Lite in a minute once we get there. So how do we convert this H5 file into TF Lite? Very easy. You already saw these 3 lines of code. So in TensorFlow, we are going to load the model. And also in TensorFlow, you have something called Lite within TensorFlow. We're going to use that, and then within Lite, TF Lite converter method, and then within that from Keras model, get the model. So basically, let's go ahead, erase everything here, all the variables, and let's clear the screen and start from scratch. Okay, now I have a H5 model. So let's go ahead and import our TensorFlow right there, and then model. Again, this is how we load our Keras model anyway, right? So you have your models.load model, and this is the model we saved earlier. So let's go ahead and load it. Once you load that, we need to convert that into TF Lite, and this is a single line right there to convert that into TF Lite. Now, how do you optimize? There are a few ways of optimization. You can go ahead and look at the documentation for TensorFlow Lite, but there is one way, one optimization is just go ahead and set this to default, okay? Again, to reduce the model size. This further reduces the model size, but I already did save this model 2 ways. I have 2 TF Lite files. So let me go ahead and open my saved models right there. I have the H5 file, which is about 10 megabytes. Again, this is not a big model, right? So 10 megabytes, that's it. And I have a TF Lite file of the same thing, which is 4.7 megabytes. And then optimized TF Lite, which is also .tf Lite. I just added, to my file name, just underscore optimized. The difference between these two is one, I just enabled the optimization, and the other I did not. That's it. Now the reason is this optimized file on Windows system, if you try to use this, it will be extremely slow, very, very slow. But on an edge device, this will be very fast. Okay, so for demonstration purposes, we can actually save this demo for our when we get to our Raspberry Pi example later on. But we'll see the implementation of all these 3 in a second. But hopefully now you understand how to save this into TF Lite. So you just have this this line to convert, and then your TF Lite model is basically your converter.convert. Okay, so that's your TF Lite model. Now, and then I'm basically saving this right there. So after this, I have these 3. Now what? Now let's go ahead and make our predictions, inference, to see how well these models are. I mean, I don't expect, obviously TF Lite is not supposed to be any better than H5. In fact, H5 is supposed to be better, because TF Lite, when we go from 9.5 megabytes to 4.7, we are losing some information. We are compromising on some quality. And from 9.5 to 1.2, that's a serious jump, right? So it'd be great if all the models perform very similar way in terms of accuracy. So we'll get there. Finally, the inference. Let me save this. TF Lite inference. How do we predict? So let's start from scratch again. So all the variables are removed, and we start from a clean slate. Okay, so let's import our libraries that we may be needing. Apparently, a couple of libraries, I'm not even using them. And then comes our image itself. Let's load a sample image. Okay, just a test image. So I'm just loading one of the uninfected images, so we can basically see how the model is performing. Obviously, the target size is 150 because that's what our model expects. So let's go ahead and load the image. And this is since I'm using Keras preprocessing.image. This is an object. This is not a NumPy array, so we need to convert that to NumPy array. Let's go ahead and do that. You can directly load the image using OpenCV. Nothing wrong with that. Okay. So now we have an image, a NumPy array of 150 by 150 by 3. Next, let's go ahead and reshape it such a way that we can infer. And you know what the reshaping needs to do, right? So it needs to add this one right there. So we have one image of 150 by 150 by 3. So far so good. Now let's go ahead and normalize our image. Again, remember we normalized our images. If you divide your image by 255, the pixel value, go ahead and do that. So this is exactly following whatever I have done as pre-processing for my training, right? So that's exactly the steps we are following right here. Okay, so now let's start predictions. First, let's predict using our regular Keras. How do we do that? We load a model and model.predict. That's it, right? So let's do that. So first of all, I added this line called Keras model size, just so we know what the size of the file is. I already showed you. The size of this is 9.5. I just want to add a print statement later on saying that, hey, this file is this much and so on. That's exactly why I added this, completely optional step. So I hope you know how to get the file size, right? So it's os.path.getSize and whatever the file size is. I'm dividing this by our megabytes. Remember, megabytes is not just 1 million, right? So it's actually 2 to the power of whatever number that gets you to million. So it is this value. So when I do that, you should see my Keras model size up here is 9.3. We know that it's 9.3 megabytes. Let's go ahead and print that for now so you guys can see it on the screen. And the model, now we are going to load the model. I mean, typically we don't do these two steps. This is just, again, like I said, I just want to print these for all of these different models. Okay, our Keras model is loaded. Now let's time the prediction. Normally we do model.predict. Of course, that's exactly what I'm doing, but I'm putting timer before and after so we can predict. We can print out how long it took for the prediction. So as you can see, I'm trying to do a few tests here. What is the size of the model? How long does it take to give me the result on Windows system, obviously? And what is the quality of the result? So these are the numbers that we'll print out later on. Okay, so the Keras prediction for this model is that this is 2 to the power 10 to the minus 8. That basically means this is uninfected image, right? I mean, is that what it's supposed to be? Uninfected. Yeah, that's good. So we're getting good prediction on this specific image. Now, let's get the size of the TF-Lite file. Again, I'm looking at 100 epochs TF-Lite file. Yeah, so let's go ahead and print out the TF-Lite file size, and this should be 4.6 megabytes. Now let's get the model path for TF-Lite and start the predictions. In fact, I probably should move these to there. Okay, now things make sense. So we started the predictions using TF-Lite. Now, how do you do predictions using TF-Lite? It's not just model.predict. Okay, that's only with your Keras, right? So how do you do the prediction? So first of all, you need to instantiate the interpreter. So my interpreter here is tf.lite.interpreter, this method. And on edge devices, you can just install TF-Lite, only inference part, and then get the interpreter from that. Again, I don't want to confuse you yet. Let's save that for the video, for our Raspberry Pi video where we deploy this onto this device. Okay, so my interpreter is basically, this is like, think of this as loading the model. Okay, so this is my interpreter. And then allocate tensors. Now it's going to allocate the tensors. And now let's go ahead and get the input details, right? So when you actually assign this to interpreter, it saves the information about what your input size is and a whole bunch of other stuff. So let's go ahead and get input details right here. So interpreter.get input details. It's going to give you, let's go ahead and open that. Let's open this, so you can see it. What information does input details store? Well, it stored what type of data you have, and index right there, and then the name, the these are all immaterial. What's useful is right here, shape. 1 by 150 by 150 by 3. So it knows that, okay, this is the type of image, this is the size of image that it is expecting. Okay, so this is important right there. And let's go ahead and do very similar thing for our output details. So now it has information about output. That's it. So now if you look at the output details, what is the dimension of your output? 1 by 1. We know that because it's either parasited or uninfected, right? So these are the two options right there. So it's 1 by 1 right there. I think that should explain bulk of it. And now let's go ahead and get input shape. We know what the input shape is. Input shape is basically input details. This is nothing but a dictionary, right? The input details, and look for the key shape and then get the NumPy array from that. So that's exactly what we are doing. Input details, get the shape, okay? And that is our input shape. And let's go ahead and print the input shape, 1 by 150 by 150 by 3. And let's get our input data. Our input data is same as our image right there after normalization. Yeah, so I'm just reassigning to a different name just so it makes it easy for us to track. Now let's go ahead and set tensor. Remember, we allocated the tensor right there, so go ahead and set tensor. By the way, if you think this is a bit too advanced, don't worry about it. Just copy these lines. Just copy these lines and then apply that to your own model. That's it. Okay, so where are we? So set tensor right there. So and it is setting this tensor with the shape of our input data right there. So let's go ahead and do that. Interpreter.set tensor. So we have input details with index. Again, let's go ahead and see what the input details and index is. Index integer 0 right there. And our input data is our image. Okay, so now the tensor is set because our image is basically a tensor. It's a two-dimensional, in our case, 2D image with 3 channels. Okay, so that's a tensor. So it did set the tensor for our input data. Now, the way you're predicting is interpreter.invoke. This is like model.predict. Okay, this is your prediction. So let's go ahead and do these lines and then print out how long it actually takes. We'll compare this in a second, but it did the prediction in a pretty quick way. Yeah, and let's go ahead and print out the output. There you go. And right now we got 2 10 to the minus 8, which is basically uninfected. Okay, so we're getting the same type of result. Now, predict using TF-Lite with optimization. So now I'm going to do exactly what I have done up here, except instead of my 100 epochs file, I'm using 100 epochs optimized file. That's it. Everything else is the same. So let's not talk too much about it, and let's go ahead and run these lines. Exactly same steps as you will see here. Let me do that up to this point. And you will see that this is going to be slow. Time before, time after, and let's go ahead and predict the time. Print out the time. So this is 0.65. It's not like this is 10 minutes. It could be, depending on the complexity of your model. But in this case, this is just 0.65. So let's go ahead and print out the output. And my output is 3 to 10 to the minus 8. This is still uninfected, obviously. So let's go ahead and print out the summary so we can just get a quick idea of what is going on here. There you go. So Keras model size, 9.3 megabytes. And the TF-Lite without optimization, 4.6. With optimization, 1.16. This is great if I can use that on edge devices where I don't have enough memory. Now, what are we compromising? Here, this is only Windows time, so I'm not sure if it's fair, to compare this, but why not? On a Windows machine. The prediction using Keras model, it took 0.14 seconds. Using TF-Lite, 0.02, super fast. Yeah, because this is not optimized. So Windows, in a way, kind of understands that. This is optimized, and it's a bit slow. I'm curious how long this actually takes on an edge device. So 0.65 seconds right there, not bad. But let's look at the final result. 2 10 to the minus 8, 2 10 to the minus 8. These two are almost identical. So the quality of results between Keras model and TF-Lite without optimization, even though we went from 9, almost half in terms of size of our model, the quality is identical. And here we compromise the quality a little bit, like it went from 2 to 2.4 10 to the minus 8 to 3 10 to the minus 8, practically the same again. It'd be interesting to check this on a whole bunch of different images to see how the quality changes. So The goal for this video, at least for me, was to communicate about TensorFlow Lite at a high level, explain why we need it, and then see how we can convert our Keras trained H5 model into TensorFlow Lite with and without optimization, and then make inference with all these three: Keras, without optimization TensorFlow Lite, and with optimization TensorFlow Lite, and then compare those. And we hope we achieve that goal here. So in the next video, let's look at facial detection and build an application about emotion, age, and gender detection, using our facial detection. I chose that example because it's easier for me to just take this web camera and then point at my face and then see how it detects, the emotions and everything. With this malarial, it's very difficult, right? I mean, it makes it very challenging for us to relate to these applications when deployed onto edge devices. So please stay tuned, subscribe to this channel, so whenever those videos get uploaded, you definitely get notified about them. Thank you guys, and let's meet in the next video.